Okay, so hi everybody. My name is Ivana Collado Gonzalez. I'm from the Robust Field Autonomy Lab at Stevens Institute of Technology. I'm a PhD candidate there, studying under Professor Brendan Englot. And I'll be presenting my work towards versatile opti-acoustic sensor fusion and volumetric mapping for safe underwater navigation. I'll try to get through it a little fast so everybody can end on time. So first of all, I'm going to just give you a brief introduction to underwater vision research, its application, industry interests, and challenges. Then I'm going to present our work, motivation, methodology, experiments, results, and conclusion. And then last of all, I can chat a little bit about learning-based approaches in underwater research and why most of them struggle a little bit. So first of all, underwater vision research has a lot of applications, including coral reef monitoring and preservation, aquaculture, fish farming, oil and gas, defense, and renewable energy, but there are many more. Industry currently relies mostly on underwater human divers, and I cannot stress this enough. This is one of the most dangerous jobs on Earth. It's super risky to do this. That is why it presents a very high cost to hire a human diver to perform either maintenance or inspection tasks underwater. And you don't just have to pay for the diver, you also have to pay for ship to transport the diver and all the equipment to wherever your offshore application is. So it is extremely costly. On top of that, human divers have operational limits. So there's only so much water pressure that a human body can withstand. So human divers have a limit of how deep they can go. On top of that, there's also a time limit of how much time they can spend underwater. And that really depends on how much oxygen they can carry. So this is why industry is really interested in the development of autonomous underwater vehicles, which could be potentially perform mapping, inspection, and maintenance tasks in a lot of different applications. However, AUVs, or underwater vehicles, also have a set of challenges. The main challenge is that they don't really have access to GPS signals, which is how, above ground robots localize themselves in their environment. So they rely on onboard sensors to localize, including inertial and velocity sensors. However, this leads to localization error or drift. And one way to mitigate this error is using SLAM, which is simultaneous localization and mapping, using visual features in your environment to correct this localization error, and then be able to perform tasks such as navigation, mapping, and reconstruction. So a lot of the underwater vision research going on nowadays, they assume that we're working in crystal clear waters with an abundance of visual features, which will then allow them to do feature detection, feature tracking, perform SLAM, navigation, reconstruction, etc. There are places on Earth that look like this, beautiful places off the coast of Mexico, in the Mediterranean, places like that. However, there's also a lot of underwater environments that look a lot more like this. So on the right, we have a clear water environment. However, there's not a lot of features in there. There's a little bit of sand that maybe you can use, but there's other cases where you're just looking out into the blue ocean, and it's very hard to localize in those cases. On the left-hand side, we have a turbid water environment. Turbid water, as is obvious, I think, it makes it really hard to see, really hard to be able to detect and track features reliably. And the thing is that there's a lot of different causes for turbid water, but two main causes are actually humans. Like, humans cause that. The first of all, it's pollution. So we cause a lot of pollution and cause turbidity. And then on top of that, also human activity. We kind of pick up sediment while we're moving around in the environment. So even if an oil gas company decides to build their structure out at sea where there's clear water, once they start construction and they start moving sediment around, they'll create turbidity. So we're basically creating our own problems. So that is why underwater research is so hard, because we're working with these very challenging and unpredictable environments. Current perception methods are highly sensitive to the non-uniform lighting, feature sparsity, high turbidity. So the creation of robust perception solutions for safe, reliable operation in these harsh conditions remains an open research problem. So now that I've set the stage, I'm going to talk to you a little bit about our work. So our main motivation is improving AUV autonomy and safety. AUVs, some tasks that they're required to perform require large-scale mapping, while others require close-range reconstruction. However, they should be able to safely operate in both clear and turbid conditions. So we aim to provide more reliable sensing and mapping solutions across diverse conditions and scales. So on the right, we see, well, we're looking at a very turbid environment here with these two little videos. On the right, even though monocular vision is usually high resolution, it is unreliable in turbid waters and lacks depth scale information, so it's very hard to use in order to plan, reconstruct, etc. On the left, technically we could use sound, which is more robust to turbidity and non-uniform lighting. So this is actual footage from our sonar sensor. And in case you're wondering, yes, it's kind of the same technology that we use for ultrasounds to see babies. So sound is robust to turbidity, however, it has low resolution and elevation ambiguity. So in order to explain what I mean by elevation ambiguities, on the left, we can see that this is the horizontal sonar view, and we have multiple beams going out at different angles, and we know exactly what angle our return is coming from. However, on the right, we can see the vertical sonar view, and even though we're getting a return, we have no idea which one of these red dots really the return came from. So we don't really know what the elevation angle of our return is. And that is what elevation ambiguity means. So that's what makes reconstructing or using just sonar so hard, because we don't really have the full 3D information. So our goal is to provide a sensor fusion and mapping method that works in diverse settings, prioritizes reliable and risk-sensitive information or close-range data, can be able to reconstruct complex geometries in real time, and doesn't require sonar datasets or multi-view data. So there's a big problem with requiring sonar datasets is that there's so few people actually working with this equipment nowadays, and even less people that open up their datasets to be a public use. So relying on a sonar dataset is really a big problem because there's really not a lot out there that we can use. So now I'm going to move on to our method. First of all, we've set up a robot with 2 orthogonal forward-looking imaging sonars and 1 forward-looking camera with overlapping fields of view. And we're going to leverage the overlapping vantage points of these sensors. First of all, we're going to perform sonar to image matching, trying to leverage the distance from a sonar range return while getting elevation from the optical image. We're also going to be performing stereo sonar matching within the limited field of view where the 2 sonars overlap. So that field of view is given by red and blue here. So here's our main pipeline. As input, we're going to take the camera image and the 2 sonar images. We're then going to perform image segmentation. As I mentioned previously, in turbid water, it is really hard to detect point features and track them reliably. So instead of doing that, we're going to detect regions of interest within the image. And we're going to do that using a very simple deep learning approach. We're going to use YOLO nano segmentation model and take advantage of just transfer learning techniques. At the same time, we're going to try to extract features from our sonar images, and we're going to do that using the SOCA-CFRAL filter, which is a variant of the constant false alarm rate technique, to detect salient features and get rid of a lot of noise and second returns from our sonar sensor. Then we're going to start our stereo matching. Again, we can only perform stereo sonar matching within the limited field of view of the 2 sonars, which is given by these red lines in these bottom images here. And we're going to match features based on range within this field of view. And this formula here in the bottom is going to give us fully defined 3D points in space. So now that we have our point cloud, we're going to project it onto our region of interest seen here. And we're going to use the region of interest to kind of get rid of maybe noisy returns. So any points that land outside of our region of interest, we're going to be discarded as noise. And we're going to keep the rest of the points and use them for the rest of our algorithm. Really important part of this method that we presented here is that in case there's no useful information from our camera, we really can't see anything, we're still going to be able to use our stereo sonar point cloud, the raw stereo sonar point cloud, and we're still going to be able to map our environment. Even though maybe it's going to be a little bit noisy, it means we're still going to be able to operate safely, even if the camera is basically useless. So sonar is sparse and noisy, so there is a probability that not all features will be detected by both sonars. On top of that, the overlap region of the two sonars shrinks as it gets closer to the robot, which means that the objects that are closest to the robot are the most probability of being missed, but they also present the most risk of collision. So instead of getting rid of these unmatched features, we're going to save them, and we're going to try to map them to 3D locations in space. So we don't have elevation information, as I previously mentioned. So what we're going to do is we're going to map them to every single possible angle that our sonar is giving us. So we're going to map them to all the elevation angles that we can. And then we're going to project them onto our camera image, onto our region of interest. So horizontal sonar features will be seen as vertical lines, as seen here in this example. Any points outside of the region of interest will be discarded as noise, but we're going to keep the ones inside, project them to 3D space, and create our second point cloud, which is our sonar to image point cloud. On top of that, we're also going to use our camera image to try to expand our sonar field of view. So sonars have a limited vertical field of view, and we're going to use this camera image to try to expand that field of view, as can be seen here in this middle image. We're also going to get rid of the points we previously used, but those projected to 3 will create our final third point cloud, which is our expansion point cloud. Now that we have 3 different point clouds, we're going to assign a confidence value to each one, depending on the assumptions that we made when we created them. So for our stereo sonar point cloud, we are pretty sure that our stereo matches are correct, so we're going to assign a high confidence value. For our sonar to image point cloud, we are assuming that points have the same depth or distance within the sonar vertical field of view. Given that this is a small field of view, this is a fair assumption, and we are going to assign a medium confidence value. For our expansion point cloud, we're assuming that points have the same depth beyond the sonar vertical field of view, which is not always the case, so we're going to assign a low confidence value. We're then going to use these confidence values in our Gaussian process mapping algorithm. In a standard Gaussian process mapping, all the points have a constant noise variance, so all observations are treated equally. In our approach, we're assigning each observation its own noise variance value that reflects the reliability of the source. So our point count confidence values are inversely proportionate to the noise values assigned during mapping. And now we're going to move on to the experiments. We did experiments both in clear water tank settings and in turbid water marina settings. So we have a couple of examples here. First of all, I'm going to show an example of our robot in our tank setting. And this is the tank we have, thankfully, access to at Stevens. In the top, we can see the 2 sonar images and the sonar features being detected, as well as the camera image and the camera image being segmented. In the bottom, we can see the final reconstruction of our structure. So here's the final result. Our approach is shown in the middle, and we're comparing it to other state-of-the-art reconstruction methods. As we can see, our approach is able to capture the changes in geometry of this structure. We're also getting good coverage overall of the scene without incorporating kind of a lot of error like the other approaches have. Now for the second example, now we're going to be looking at also in the tank, but 2 very similar structures, which can be very challenging for sonar, using sonar in this case. Again, in the top, we can see the 2 sonar images and the features being detected, as well as the camera segmentation. And in the bottom, we can see the final reconstruction results. For our results, our approach is shown in the middle, compared to other baselines. Again, we can see that our approach is able to capture the changes in geometry of both structures. We have a reasonable coverage of the scene without incorporating just extra erroneous information. I'm going to show our testing in the marina settings, and this is highly turbid water. We're going to be looking at these wooden pier pilings. So again, at the top, we have this sonar information, the camera information, and the bottom, we can see the 3D reconstruction coming to life. Some of the pier pilings are diagonal, so you're going to be able to see some of the diagonal artifacts coming into view in the 3D reconstruction below, as can be seen here. All right, so this is the final reconstruction that we were able to obtain. Again, some of the pier pilings that we're looking at are diagonal, and we can see the diagonals here in the reconstruction clearly. There's also two very, very small metal pipes sticking out in front of the pier pilings, and we were able to capture those in a reconstruction, which I believe is very impressive because other algorithms just were completely blind to them, and they were the most risk of collision with the robot. Also, we're able to keep some of the background information. Even though it looks kind of noisy, this information is extremely important for an autonomous robot trying to perform path planning in this kind of cluttered environment. So in conclusion, our algorithm outperforms a lot of state-of-the-art methods in accuracy, and we're able to map very complex geometries while keeping good coverage. Also, we can map structures of varying scales, even in low visibility conditions, and we prioritize critical close-range data to enable safe navigation and manipulation. So for future works, we plan on incorporating maybe dynamic environments, improving our sonar camera calibration strategy, and maybe trying to do a more adaptive sensing or adaptive changes of our confidence values depending on visibility conditions. So that's it for my method, but I thought it would be interesting to just chat a little bit about learning-based approaches and why they're very challenging for underwater research. There is a lot of methods trying to synthetically correct for turbidity, and so trying to correct the dehazing or color correction. However, we don't really have ground truth, clear versus turbid ground truth. So that really means that we are completely reliant on unsupervised learning, which creates kind of a training instability and causes hallucinations. Also, because the water presents such a different physical model every time you change kind of the wavelength or one of the many factors that contributes to turbidity, a lot of the models end up failing or just overfitting, so failing when you try to change them into a new environment. On top of that, most of these approaches are too computationally expensive to work in real time on an onboard computer. For a different kind of research very relevant to what we're doing here is monocular depth estimation. However, because of turbidity and other things in the water, such as backscatter and moving marine life, just kind of self-supervised approaches that attempt to do this are really failing because of just there's no consistency across samples. And on top of that, it's really hard to model. There's a lot of optical distortion when trying to put a camera inside of kind of a canister underwater. You get a lot of warping because of the ports that we're looking through and just the changes of the lens that extra glass gives you, which causes a lot of geometric errors in reconstructions and depth estimation. For sonar 3D reconstruction, the elevation ambiguity, just kind of the loss of 1 degree of freedom, trying to invert the 2D images provided by the sonar back to 3D is just a very ill-imposed optimization problem that's extremely hard to solve. On top of that, we don't really have a lot of data to work with, as I mentioned previously. And we have a lot of different types of sonars, not just one. So we can't really generalize one sonar to the next. We really have to be very specific about the kind of data that we're using. And sadly, the simulators are getting better. They're really, really getting better. There are a lot of people working on this. However, it's still really hard to have a realistic synthetic data from simulators. On top of that, most 3D reconstruction methods that use learning are not really viable for real-time execution quite yet. Maybe someday. And then for the multimodal fusion, which is kind of what I presented today, there's a lot of data scarcity. Again, if there's scarcity before with just sonar data, getting sonar data paired with camera data in a data set is extremely hard. And then also you add the calibration complexity into the problem of how do we calibrate a sonar which has elevation ambiguity with camera returns, and it's just a very, very difficult problem to solve. On top of that, the few works that use learning to solve this problem are usually neglecting just kind of turbidity. They're just assuming we have clear water. Hopefully that'll change soon, but it's still a very hard problem to solve, even in clear water. And the few that do exist are too computationally heavy for real-time embedded deployment on the field. So that's it for me. Feel free to check out our lab website with all the links to the papers and the videos and everything. And I hope you found this interesting, and let me know if you have any questions.